Hello, welcome back to the videos, to the channel. We're continuing working on trusses, and today I just wanted to introduce it. We're going to be working on the same truss as we did in my previous video, and so I'm going to link somewhere up here that previous video where we work out the reaction forces at the start, and I'll reiterate that again. What we're going to do is just come back here and click to here, and we should now be seeing the right thing. Right, there we go. So we're going to be looking at method of sections to determine forces in a truss. This is still Unit 27, it's still outcome A. It's a much quicker method, but we don't work out all the forces, and so it's often used where you've only got one or two forces to calculate, and we're going to use it. I've set my students the task of working out 6 members within the centre of the truss to verify their answers from the previous truss. So just to remind ourselves, we're going to look at what that previous truss looks like, which looks like this one. And as you can see, I've already put the reaction forces in. Like I say, my previous video shows how to calculate them, so if you're unsure, go back, view that video, and we'll get to this point. Okay, so what we're looking at is, what we're going to do is somewhere we're going to section our truss. Okay, we're just going to split a line and section it, so something like this. Okay, so I've picked to section it between BC, GH and BG, and that will give us 3 forces to work out. Okay, hopefully we're going to get the same forces as we got using the method of joints. Okay, because we should be calculating that. Now, once we've split the truss up, I'm just going to go and show all the forces again. So we had this as our point forces. Okay, we can see we've got BC, BG and GH on both sides of the split. Okay, we're going to use the equations of equilibrium, the 3 equations of equilibrium, to determine those 3 forces. Okay, now what's important about this method, and what we should be aware of, is that we can use either side of the split. Okay, so if you can see one side of the split is simpler than the other side of the split, then it's quite difficult with all these forces in. I'm going to modify it as we go through, I think. We shall pick the simplest side, and now I'm looking and I think the left hand side is more straightforward, so I think we're going to use that side to do our calculations. Okay, just to remind you, if you've not seen the previous video, all my members were 2 meters long, so the horizontal and vertical members were 2 meters long, making all the angles in my truss 45 degrees. Throughout this example, I'm also maintaining the convention that up and right are positive, and for the most part anti-clockwise moments are positive. Okay, that's what we're going to stick with. If we always stick with that method, we always get things right in our heads. We know what we're doing. So if we look here, I'm going to use our first equation, equating the horizontal forces. Sum of forces in the x direction is equal to 0. And if we look in that, what we've got is BC pointing horizontally to the right, we've got GH pointing horizontally to the right, and we've got the horizontal component of BG pointing horizontally to the right. And so we can put all that into an equation. BC, horizontal component of BG, and GH, all positive, or pointing to the right. Now that doesn't help us an awful lot at this point in time because we don't know what any of those three forces are. Okay. So we move to our next equation, which is the sum of vertical forces. Okay. Forces in the y direction. I cut this off slightly, it's equal to 0. I've just noticed that with my video. I do apologise for that. And if we look at that, then we've got two forces in the y direction. We've got the vertical component of BG, which is pointing down, and we've got the 2.5 kilonewton reaction force at A pointing up. So we get this equation, which becomes relatively straightforward to solve. BG sine 45 is equal to 2,500 or 2.5 k, and BG is therefore equal to 2.5 k divided by sine 45, which gives us 3.54 kilonewtons as our force BG, which if we go back and look at our previous example is what BG calculated to in that example. So we've got BG, so we could fill BG in here, but we're still missing BC or GH, or both really. So we still can't use this equation for anything. So what we're going to do is we're going to use the third equation of equilibrium, which we don't use in the method of joints. Okay. Apart from working out the reaction forces, which is the sum of moments. So if we look at the sum of moments, it is the force multiplied by the distance it acts from the pivot. Okay, posh word for pivot, the fulcrum. Okay, I have just removed all of those internal forces because they were bothering me, they were annoying me. They were also confusing the diagram. All we care about are these three forces at the section. Okay, so what we're going to do is say that the sum of all moments is equal to 0. For a moment to operate, we have the force multiplied by the distance it is acting from the pivot. We have to make sure it is the horizontal or the vertical distance. So we are not moving this distance to point B, we are moving horizontally or we are moving vertically. Okay, so if we look at this, the 2.5 kilonewton reaction force, if we take moments about A, the 2.5 kilonewton reaction force will have 0 effect because it is acting on the pivot. There is no moment. Similarly, force GH is acting in line with the pivot. It's just going to try and pull the truss horizontally, so it has no moment force. So it's only the forces at point B are going to cause the moments, and there are 3 of those. It looks like there are only 2. There are 3. Excuse me. BC acting 2 meters vertically from the pivot. So horizontal forces act vertically. Okay, so we've got BC times 2 meters. Added to that is the horizontal component of BG, which is BG cos 45. Also acting 2 meters vertically from the fulcrum. Added to that, we have the vertical component of BG, which is acting downwards. All are going to be trying to turn this truss clockwise. However, sorry, I said my convention was typically going to be anti-clockwise moments are positive, clockwise moments are negative. In this case, I can see through looking at this diagram all my moments are going clockwise. So I have made the decision to modify my standard for this calculation alone and just make everything positive. rather than making everything negative. So we have BC acting 2 meters vertically away, horizontal component of BG acting 2 meters vertically away, vertical component of BG acting 2 meters horizontally away. Okay, whatever the length of your members, this distance will be relative to that length. Okay, if we work that out, we know that BG is 3.54 kilonewtons. We've just worked that out. So we drop that in. 3.54 cos 45, 3.54 sine 45 times 2 gives us that 2BC is equal to 5k plus 5k. And hopefully you're all very good at this. We're going to work out that BC is equal to minus 5 kilonewtons. Once again, matching very favourably with the force we got when we did the method of joints. So 2 of the forces we've checked are currently happy with their work. So now let's go back. What we need to do is go back and look at our sum of forces in the x direction. And again, I've covered up my BG. I need to check that more carefully next time. We know that's 3.54 kilonewtons. We know BC is minus 5 kilonewtons. Plug them into our equation, and what we get is minus 5 plus 3.54k cos 45 is GH, plus GH is 0. Rearrange it, and we get to GH being 2.5 kilonewtons. Okay, those 3 members have now been calculated. That is the basic premise of the method of sections. If you're being asked to calculate a single force in a single member within a large truss, this is the most accurate way to do it. Okay? Because the method of joints is longer, but also each force here we calculate, AB, AH, we round those forces. I've rounded them to 2 decimal places typically. So each rounding adds errors. So if we're coming through to CD, EF starting at point A, then we've got 4 or 5 different lots of rounding errors all cooking in to the problem, making our values slightly less accurate. Whereas if we use the method of sections to work out BC, and we literally start with BC, then there's only the rounding of BG, the rounding of GH go into the make BC. We've got 1 section of rounding errors, so we are more accurate. Okay. Typically with this, you'd be asked to be sort of working out the stress in one of the main support members to see if that member can withstand the truss. Okay. I have set my class a task to use the method of sections to check 6 of their values in their assignment. So I'm going to repeat this process for another section of the truss, just to make sure we do my 6 and my students can do what they do. You make sure you do the correct number of calculations your tutor requires if you're just using this as a reference sheet. Okay, we can split anywhere we like. We just need to make sure that we split a maximum of 3 members. So I'm going to look at my truss again, and I'm going to split it. I think may as well go next one along and split it between C and D. So I've got a CD, CF and FG as the 3 I want to calculate. Once again, get the forces in there, and I'm going to now, just to show what's going on, I'm going to work on the right hand side of this, just to show we do get the same principle. It's actually slightly more complicated because there's 2 external forces. Okay, but we can Hopefully, also we've got negative and positive forces going on quite a lot, so it makes for a slightly better task. So what we're going to do is we're going to start and we do exactly the same principle. Sum of the horizontal forces is equal to 0. Looking at this, CD is horizontal, pointing to the left. FG is horizontal, pointing to the left. And CF, horizontal component of CF, is also pointing to the left. Using our convention that left is negative, right is positive, everything is negated. I want to keep this convention in this case because we've got some pluses and minuses for the vertical forces that if we start flicking our convention for one section of this task and not for the other, it will throw sign errors into the problem. Okay, so that's what we're talking here. So if we look now, again, we can't do anything with the horizontal forces, so we'll equate vertical forces. So 7.5 kilonewtons upwards is positive, plus the vertical component of CF, minus the vertical component 10 kilonewtons, because 10 kilonewtons is acting downwards. Okay, so if we look at that, we can see that CF sine 45 is equal to 2.5k minus 10k plus 7.5k is minus 2.5k. Take it other side of the equals, we get plus 2.5k. Divide that by sine 45, again CF comes out exactly as we had on our method of joints. Okay. Once again, we'll now take moments about E this time. So what's interesting here is FG is in line with E. The horizontal component of CF is in line with E. So the horizontal component of CF has no job in this calculation. The vertical component of CF, however, will do. This will be trying to turn it clockwise. This 10k force at D is going to try and turn it anti-clockwise, and CD is going to try and turn it anti-clockwise. So this time we're sticking to our anti-clockwise is positive convention, where we see that CD times the 2 meters it is acting vertically from point E plus the 10k times the 2 meters it is acting horizontally from point E minus the vertical component of CF, which is CF sine 45, times the 2 meters it is acting horizontally from point E. Plug in our numbers here. We know that CF is 3.54k, we've worked it out, and we know CF sine 45, we should know by now, we've done it enough times, is 2.5. 2CD, 2 times 10k is 20k, so 2CD is equal to 5k minus 5k taken the other side is plus 5k, plus 20k taken the other side becomes minus 20k, so we get 5k minus 20k divided by 2, which is the 2 multiplying by CD there, to get that CD is 5k minus 20k over 2, which again gives us minus 7.5k for CD. Again, what the method of joints gave us. Now we can put this force and our CF force back into our sum of horizontal forces. Plug those numbers in, so we get and this is where we need to check with minuses, minus 7.5k minus FG minus 3.54k cos 45. Again, we know this is 2.5k. So 7k minus Fg minus 2.5k is 0, which means Fg is 5 kilonewtons. 6 forces calculated. And if we go back through this video and we look at our truss, you can see that those 6 forces all equate 5k in compression, 3.54k in tension, 2.5k in tension, 7.5k in compression, 3.5k in tension, 5k in tension. That matches exactly what we were looking at. That is all the method of sections is asking us to do. It's very straightforward questions. Pythagoras' theorem is your friend with it. Okay. Hopefully this video will help because you can go slowly through it, make sure your calculations match, make sure your forces are in the right direction, and make sure that you stick to your convention. I shall see you next time. I'm not sure what we'll do next time, probably some work on bending moments, but that will be me done for tonight. Have a good night. I shall see you soon.